toast.
Well, I'm sure that you'll all remember that a few weeks ago Graham, aka the RadioCruncher, he sent me some transformers because he'd been repairing a valve radio, and unfortunately he couldn't get it to work, and it turns out that it was the output transformer that had gone open circuit. Now one of our radio friends, Sean from the Man Cave workshop, he'd also sent him another transformer as a spare, but unfortunately that had gone open circuit as well. And of course these speaker output transformers, they're quite a common failure that they do go open circuit. And the main reason that they tend to go open circuit, well, there's a couple of reasons. Probably the biggest reason them for going open circuit is that the windings on the primary side, they're actually very, very fine windings, and what can happen is the grid coupling capacitor on the output valve, that can tend to go leaky, and so the output valve draws excessive current through the transformer and burns it out in short order. The other thing that can cause damage to the windings is failure of this capacitor here, because although it's kind of primarily there as a tone control, it rolls off the high frequency, it actually also does a job of suppressing some of the higher voltage transients that you can get building up in this transformer. And of course another failure mode as well is if the radio has ever been run without the main speaker connected, you have quite a large impedance mismatch, and again that can cause failure. So what I plan to do is just open this up and have a go at unwinding it. So like most transformers, this has got a primary and a secondary winding. Well, the winding that you see on top there, that's actually the secondary, because this has got a relatively thick wire, and of course it feeds into a relatively low impedance speaker. So this has got quite a thick wire because it carries heavier current, whereas the winding inside, and we can't see that at the moment because this outer secondary winding is wound on top of it, that'll be much finer. So on that basis that the primary winding is so much thinner, you can pretty much predict that 99% of the time that it will actually be the primary winding that's gone open circuit. So let's just try this one. So that's obviously the secondary, because I think I can see it. No, it's that way around, I can see it. So this one will probably be fine. So that's measuring 1 ohm, so don't exactly know what it should be, but again, it's in the ballpark. And the secondary, the finer winding, well, it's actually showing something. It's showing 20 megohms, so it's not actually showing open circuit, but that isn't correct. And in fact, if I actually just kind of touch it and squeeze it, you can see that the resistance changing all over the place. So there's definitely something wrong inside this transformer. Now it would actually be quite accurate and fair to say that I don't know particularly much about rewinding transformers. I've only actually ever done one in my entire life, which was on a Cosa radio that I restored a few months ago, and that was an intermediate audio coupling transformer. So I'm kind of in unknown territory. I mean, I've done one, but certainly it doesn't make me any kind of an expert. So I'm just going to go ahead now. I'm just cutting the windings off the tag board. I was going to unsolder them, but there doesn't really seem to be a lot of point in that, given that they're damaged. So you can see that we've got traditional kind of E-core, I think you call it an E-core lamination, don't you? There's E-cores and I-cores. So here's a stack of them there. Usually I manage to cut my fingers open on these, and these are quite rusty. So that's another reason why it could have failed, of course, because the windings are so fine. They could have just kind of corroded away inside, because it really wouldn't take much. Now the problem is always, I was going to say, trying to get these cores off the laminations, but, well, that was really hard, wasn't it? So what that has left us with is the outer frame of the transformer, which clamps the laminations together, and that's got the tag strip, which is just looking at that, riveted to it on the top. We've got these, I'm going to call them E-core laminations. I think that's what you call them, E-cores. So normally when these are installed in the transformer, they would be sat together like that, because what that forms is a magnetic circuit where the magnetic, I'm going to call it the magnetic flux, it can actually circulate round. If you actually remove these, the magnetic field can't circulate, so it wouldn't actually work very well as a transformer. So these do form a very important part of the transformer. It certainly wouldn't work without them. And, as I mentioned before, you can see there's lots of little thin slivers of metal. Well, these are, again, it's laminated, it's a laminated core, and the reason that they laminate it, it's to reduce what they call eddy current, which is one of the forms of losses within a transformer. And these windings are actually wound on top of a bobbin, and you can see that's this square thing, and that's made out of something like, I think they call it a peroxylin material, which is, it's either paper which has been compressed or cotton sheet that's compressed, and it's compressed under high temperature to form along with some what they call phenolic resin, which is kind of the main ingredient in Bakelite material. So it forms a very good, very stable and very strong insulator, and they've actually made like an open-ended rectangular former here, so that's what all these windings are wound onto. So just looking at this wound bobbin, I'm immediately a little bit confused, because I was actually expecting the windings to start from that top outside layer, but these thicker secondary windings, they actually appear, I'm not going to be able to get it on camera, but it's not starting, it's not the end, the wire lead isn't coming out at the end of the winding. It appears to almost be coming out of somewhere in the middle of the winding, and I don't really understand that. It's almost as though it's been wound with something like a humbucking coil or something, but I don't think that's the case. Certainly the resin or the sticky tape, whatever it is that's on here, it's really, really strong stuff, really thick stuff. Now, for reasons that I don't fully understand, you can see that one of the windings here, which is actually the start of the winding, and I said it was coming out of the middle there, well, it's actually just looped under a bunch of the other windings, so I don't know why they do that. I'm hoping that'll come out on camera. Can you see that? If I just push that, it actually does now emerge from one end. So what I need to do I need to count these off. 1, 2, 3, 9, 10. And what I'm going to do is I'm going to make a note of these, because there's nothing worse than getting interrupted and forgetting where you are on the count. I've got absolutely no idea how many windings we're going to get on here. 1, 4, 2, 5, 6, 7, 8. 1, 2, 3, 4. 4, maybe 5. So the secondary winding, which would be connected to our speaker, that's got 75 turns on it. And then it would appear we've got quite a thick insulating layer on here of, well, really, it's just really horrible, gooey, black stuff. Now I am going to try to unwind this primary winding quite carefully, because you never know, we might get lucky, we might find it's broken just a few turns in, and if it is, what we'll probably do is just actually cut a few windings off it and put it back together, because it should still operate. I'm afraid all this gunky horrible stuff is going under my nails. Oh right, okay, is that burnt? It looks burnt. It could just be tar. So I'm just looking at the way that the leading wires go into this now. So this wire on this side, this is the one that was wound on first. I can see it actually goes right to the inside of the bobbin. Just going to move that down there. because that's another common place that these can fail. These can sometimes fail where they just wound onto the connecting wire, because the lead out wire that leads out to the tab, it's actually a lot thicker. The actual winding here, you can only just see it, you probably can't see it at all, it's like a hair, it's very, very fine. Whereas this wire that you can see here, it's not actually the winding, it's just a lead out wire, which is obviously stronger because the winding is so thin. They're very easily damaged, so they don't take the winding out, they just take a lead out wire, and that's soldered onto the tag board on the transformer. So I'm not sure if you're going to be able to see this, but we've now exposed a very, very fine winding, and we could actually start to unwind this now, but I'm not going to unwind this by hand because there's going to be too many turns on it to count. So what I am going to do is I'm going to well, I need to actually make a former which fits inside here, which we're going to put it on a winding machine, so we're going to use that former to unwind it, and we're also going to use that former again when it comes to winding the new windings on. So I think that's what I need to go away and do next. I need to make a wooden former to actually go inside this this bobbin, and something that's going to be a tight fit inside there. And I've just sprayed a little bit of deoxit chemical on here. I probably could have used WD-40 because I just wanted to know what the solvent was for this this gooey material. So it does appear that a petroleum product will actually dissolve the resin that it's covered in, because what can happen is when you try and unwind it, because it's got all this goo on top of it, it can actually stop the windings coming off. It can get them caught, and they just constantly break. So what I did with the other transformer that I unwound, I actually had to cover it in acetone, but this one I think will come off okay. So we've probably taken about 4 or 5 windings off on there, so I'll just make a note of that, and we'll come back when I've made that former. So I think we'll let that sit in some WD-40, and maybe that'll help to free up the goo on it. So we've got all our wire off now, and I just need to take a measure of it. So that's coming up as diameter as 0.42 millimeters. I'll just measure it in a couple of places. 0.42. Now I have gone ahead and I've actually stripped off the enamel insulation on this, because when you buy the wire, they actually specify it's actually the wire diameter, it's not the wire diameter plus the insulation, and that's actually caught me out on more than one occasion. So I've cleaned off the enamelling. Yeah, 0.42. Now this one being such a fine wire, I think it's probably going to be harder, if not impossible, to clean the coating off it. I was just trying to give it a scrape there, and I've actually just cut it. Oh, done it again. So with the enamel insulation on the winding, it's measuring 1/10 of a millimetre. So you can probably hear in the background I've got the 3D printer going because I'm printing out an end cap to actually go on the mandrel for when I have a go at rewinding this transformer. Just to make the point, I actually don't know very much about winding transformers. I'm kind of learning by my mistakes, so I'm not necessarily saying this is an example of how to do it because I'm just winging it. Here's the original transformer we're going to rewind. Now you can see it's got an inner plastic Bakelite former. But the problem is it hasn't got any end pieces on it, so I think if I try to wind this, the wire will just fall off once I've rewound it. Whereas if you actually look at the way this is constructed, it actually hasn't got any end pieces on it, but the each of the windings seems to be embedded in a kind of a waxy layer of tape. Unfortunately I can't show you that without dismantling it, but there's no solid wings, there's no end pieces on this. So I think what I'm going to try to do is, I think I do need to try to put some ends on this to actually form a bobbin rather than this kind of open section rectangle. So we're going to try and put some sides on this. So what I'm going to try to do is, in fact probably a better example is I've just got a piece of paper here which I've just printed off some cardboard templates. I'm going to use these as a template and then actually cut these side pieces out of cardboard, but if I just cut this one you'll get the idea of what I'm trying to do. So what I'm going to try to do is I'm going to get some pieces of cardboard, this is just paper, but I'm using these as a template. I'm going to make some end plates out of cardboard and I'm going to try and glue these on, and what I'll probably do is I'll probably paint some dope material onto them to try to stiffen them up a bit. I think this is quite stiff paper, but I don't think it'd be quite thick enough. But I have got some cardboard that I'm going to use, so there'll be one of these end plates on either side, and that's hopefully going to form a bobbin. So here's my Wilko's quick glue stick, which is not even, well, I'm going to say not even slightly sticky. Oh, that's rubbish, isn't it? Does it get any better if we cut the end off? Oh, that is totally crap. Well, I did in fact get a glue stick with my 3D printer, so this is designed to stick down a print bed, but everybody tells me it is just glue stick, so let's just see if it will stick down a piece of paper. Kind of an interesting bit of reverse engineering, actually using a glue stick for what it was designed for. So okay, this is stuck on here now, so now what I need to do is I need to try to cut these out. As I say, I've got no idea if this is right or not. I'm definitely in the territory of winging it. I could be doing it totally wrong, but you know, you got to live and learn. Even if I make a mess of this and get it totally wrong, I'll probably learn something in the exercise, and no doubt you guys will leave it in the comments, you people who've wound transformers before, and you'll say, well, you shouldn't have done it like that, you should have done it like this. So I've got some of this acrylic conformal coating. Well, I'm not sure, but I'm hoping I can use this to actually glue my little cardboard assembly together. I don't know, we'll give it a try. I'm hoping I can just push this through. Okay, that's gone through, and yep, it certainly does feel sticky. And I'll just take the opportunity to put a coat of that stuff on this side. I think we'll let that one dry, then I'll turn it over and do the other, and then I'm going to put a few more coats of that acrylic on it. Well, I've got to admit, this first part is one of the parts I'm most worried about, which is actually soldering this rather thin enamel wire. I've got to solder it onto the actual, well, it's got a leading wire on that I've put on the bobbin, which is much thicker. So what you've got to do is you've got to solder the very thin wire onto this slightly thicker one. Now normally what I like to do is, if the other end of this, I've got a bobbin of brand new enamel wire here, well generally if you're lucky what they actually do is the other end of the wire will be sticking out, so when you've actually soldered it on you can do a continuity check from one end of the wire to the other. Unfortunately, because the people who've round this wire for me, they haven't done that, So unfortunately I've just got to kind of solder it on and, you know, trust to the gods that it's going to be good. Trim the end off. So I'm going to grab hold of the wire using a piece of cloth, because one, it makes it slip through my hands a bit easier, and two, I don't want it to get covered from sweat off my hands. And the bit that's far hardest, it's the starting and stopping is the hardest bit. And now I've got to try and start the drill. So I'm on to 2000, I've got 1156 to go, and I'm going to put another layer of tape on. Okay, so we've got to put 3156 on here, and I put 3154, and I think I'm probably going to call that about good. Okay, that's coming up as 500 ohms, so I'm guessing I have got a good connection on there. Now unfortunately I have actually got to take this out of here now. Reason being is that I've got to actually make a little hole in the side of the bobbin core to actually take the feed-in wire through. So hopefully you can see that that's our primary wound. I'm hoping that we have got enough room to get the secondary wire on. I think we will have, because there's only 76 turns on it, so I think it was only a couple of layers. It may even have just been one layer. But as I say, I've just got to unmount this now from its mandrel, because I've got to try and make a hole in the side of here to take the wires through. So yeah, let me do that. Hoping you can see that okay, but this is what we've wound so far, which again, it's just the primary. So I'm now going to attach the other feed-in wire. And to try and get that wire in, I've just got to try and punch a hole here in the former. Hopefully I've done that without stabbing the windings underneath. Let me have a closer look. Now in the past I think people have told me that it's usually better to use some very thin multi-stranded wire to do these feeding wires. Well, I've got to admit I'm not doing that today. The main reason is because I can't find anything particularly small enough. So I'm using this single core, and I think this is wire wrapping wire. I think I would have found it easier if I'd used some slightly thicker feed-in wire, because the problem is as I'm trying to wrap these two wires together, the one I'm trying to wrap it round is just bending out the way. So I think another bit of a fail here, something to remember for the future, to use a slightly thicker wire. Oh, I managed to get a really big blob of solder on there, which I definitely didn't want. So here we go, I'm back now for the final 75 turns, and this wire is an awful lot thicker, and again I think the problem will be just getting started. I think I need to do something with the speed controller on this drill because it starts off a bit too rapidly. Oh, cock. Now all the other transformers I've built, I've actually put lead in and lead out wires on it, thinner ones, but I haven't done that with this one. I'm actually just taking out the secondary wire and I'm going to connect that to the tag strip on the transformer, and the reason I'm doing that is simply because that's how the original was done. I don't know if that's good, bad or indifferent, but I'm just following what they did. So I'm just trying to stab the hole for the output wire now. I think that'll do it. Oops, it said dropping it. So I've got to feed this out of here now. I'm actually thinking that all this feels a bit vulnerable at the moment. I'm going to try and glue it together with some of that dope stuff that I've been using, this acrylic conformal coating, because I think that might just help stabilise these windings. Well, I'm hoping you can see I've given my transformer several coats of this acrylic conformal coating, and when you actually brush this stuff on, it's really thin like water, but the solvent in it quickly evaporates off and it leaves quite a tough surface finish. So I'm hoping that if these windings were at all loose or anything like that, any insulation problems, I'm hoping that this will have soaked in, and I'm not going to say it will have fixed them, but hopefully it should prevent any problems happening in the future. So the next thing to do is just go ahead and put some cosmetic tape over the surface of this last winding just to make them black, because that's what the original transformer looked like. So let me do that. Well, as per usual for me, I've managed to grab defeat from the jaws of victory. Of course, I was meant to have a set of windings coming out of this side of the one side of the transformer and the opposite side, so it could line up with this tag strip. But of course, I managed not to do that. What I actually did was I had a set of windings coming out of the bottom here, one end, and I managed to get a set of windings coming out the opposite end, which is you know, no use whatsoever. You might not be able to see them because I've done my best to camouflage my mistake by painting them black. So what I've had to do, I've actually had to just wrap these windings. Luckily I left the leads pretty long, so I've just wrapped them around the outside and put some tape over it, and we're never going to discuss this again. So yeah, that's that done. So I've got to reassemble this now. So we've got the windings here, and well, yeah, I guess I'm just going to reassemble it. I don't think it matters which way around it goes. So these are all the E laminations. I think they may have like a coat of insulation on one side. I'm not exactly sure. You can see this green stuff that's on one side of them. Well, I don't think that is just corrosion. I think that is some kind of coating which is on there, and I can only assume that the purpose of that coating is it's probably some form of insulator which is to help stop the build-up of eddy currents. My form is perhaps just a little bit wide, and it's just catching on these sides here when I push the laminations down. It is going. Let's keep going. And before I forget, we got something very important. It just looks like a piece of cigarette paper, this, doesn't it? It's just a very thin piece of paper, and I have actually written shim on it, and that's it is actually a vitally important piece of paper, this, by all accounts. It's actually designed to make the transformer less efficient, which is a bit of a strange one, isn't it? Because normally we want transformers to be efficient, but in this case the whole purpose of this shim is to actually make our transformer less efficient. And the reason we want to make it less efficient is because I believe it's to stop the core from saturating, because if the core does saturate, I guess it stops acting as an inductor, as a transformer, and starts acting as a resistor. So that what this shim does, it helps to, I guess it helps to dissipate the magnetic field. So a little bit of a strange one, that you want to make the transformer less efficient, but you know, apparently you do. Yeah, it's going. So I think in theory that's it, and I guess it gets pulled together a little bit when you put the mounting screws in the bottom of it. Well, hopefully we haven't got much left to do now, so just got to solder these on, and hopefully we can then give it a test. I'm not exactly sure the best way to test this, to be quite honest. Well, as you can see, I've got my transformer fully assembled now, but before I actually send it back to Graham, I think I just want to do a few basic tests, because I don't want to post it back only to find that I've built a dud. So we need to do a little bit of testing. So I think the first test I will do is just, I'm almost going to call it mechanical testing. Let's just make sure that we don't have any short circuits between the windings. Okay, and that's coming up at infinity. So at 500 volts, we get a reading of infinity, so very high resistance between the primary and the secondary, which is good. So let's just now test between the, what is that one? That's between the primary and the case of the transformer, the metal work. Again, we should have infinite resistance. 999 megohm, which effectively that's infinite, isn't it? Let's go on the other side now, which is secondary to the casing. Again, infinity, 999 megohm. And of course, just like to test my meter reading. Okay, 0 ohms. So that's all good. So in terms of the insulation between primary, secondary, and the connection to the chassis of the transformer, all that's clear, so electrically that is good and safe. While I've got this meter on the bench, I'm just going to take a measurement of the secondary resistance. I'm going to measure them both, the primary and the secondary. It's just that this particular meter is good at the very low resistance range, although it probably won't measure the primary, because the resistance will be about 500 ohms, and I think this only goes up to, well, I think it goes up to 100. Anyway, let's measure the secondary resistance. We're expecting this to be very low, maybe less than an ohm. Okay, so that's half an ohm. Let me just check I've got the test leads as well as it could be. Let's measure the primary now, and I think in theory this should be around the 500 ohms mark. That's what I calculated. Okay, and that's coming up as 518 ohms for the primary, so I'll make a note of that. So it looks like our transformer, it's electrically safe, and the windings kind of look okay, but the important thing is, can we get any sound out of it? So I've got a speaker here. Now this transformer is designed to go into a 3 ohm load. Now I've got this speaker. Does it say what it is? No, it doesn't tell me. I suspect that this is probably it's probably 4 or 8 or maybe 16 ohm, I don't know. I can actually check it, because I've actually got an impedance meter on the bench here. So should we do that? So this piece of equipment here is designed, actually, it's just an impedance meter like you get for measuring capacitors and inductors, but this one is designed to work at you know, lower audio frequencies. So I've just connected that to the wires, the input jack to the speaker. Switch this on. It's on the 200 ohms range, so I think that should be right. So just press the test button, and that's giving me a reading of 8.8 ohms. So I should probably write that down, because I'll forget if I don't. So this speaker we've got here, it's an 8.8 ohm speaker. Make sure I get it the right way around. So this is the input side here, that's the primary. Now I don't think this is going to sound particularly loud for a number of reasons, because this is quite a big step down. It's in the region of 40 to 1. So any signal that we put in here with a signal generator, it's going to get reduced by well, it's going to get divided by 40 before it even gets to the speaker. So I'm not expecting we're going to hear very much. So 1 volt. We're on the 1K setting. Let's turn up the amplitude. Actually, that's not too bad. Can you hear that? Let's do a quick frequency sweep. Let's hope we can annoy the cats and dogs out there. Okay, so I can hear that up to about 10 kilohertz. Now I don't know if that's the speaker that's got, you know, the audio bandwidth is probably limited, because this is probably a mid-range speaker. But maybe that's my hearing. I'm getting on now. I'm getting old, so I'm not a young youth. I can't hear up to 20 and 30 kilohertz anymore. Maybe you can. Can you hear anything? Can you hear that? Turn it off. Turn it on. I can't hear that. I can hear that. I can hear 9 kilohertz. That's quite annoying. Can you hear that? I'm not exactly sure how loading up videos and how YouTube will process these high frequency sounds. I don't know whether it'll be compressed out. I'm not sure. Let me know if you can hear that. So that's 9 kilohertz. 8, 7, 6, 5, 4, 3, 2, 1. Let's go into the hundreds of hertz range. Alright, back at a kilohertz. 800, 700, 600, 500, 400. That seems to be going down in volume now, that. 350, 300, 200. I can still hear that, but it sounds very low in volume. Okay, I lose that at about 150 hertz. I can't hear that anymore. So that's a good sign. This speaker is it's definitely working. Now I suppose some of you might want to see a slightly more scientific test. So you can see I've got a scope lurking in the background here. So what we'll do is I think we'll do a frequency sweep on it, and we'll just have a look at the actual bandwidth of this. I'm going to put a load across the output of the transformer. I don't know if we should do that or not, but I am going to. So here's a load, which is it's a 3 ohm load, just a couple of resistors soldered together. And now I'm just going to measure the output. So again, we're on the secondary side now. Let's connect that up to the scope. Okay, so on the top of the screen here we've got the yellow one. That's the actual input from the signal generator, and on the lower one we've got the output, the secondary of the transformer. I'm just going to tweak the signal generator down a little bit, because I know from experience that this signal generator can't maintain its output at very low frequencies. So I'm going to turn the output down to 3 volts. Just looking at the output here, it's around 53 millivolts. So I'm going to take that as my 0 dB's reference, and what I'm going to do is I'm just going to increase the frequency until we get 70% of that, because that's going to be approximately 3 dBs down, isn't it? So we're going to be keeping the input to the transformer constant at about 3 volts, and we're going to rock the frequency backwards and forwards until that comes down to about 37 millivolts, which is going to be the 3 dB point for calculating the bandwidth. 37 millivolts. So it looks like the upper frequency, our F2 for this transformer, that's coming out at 12.7 kilohertz, so I'll make a note of that. So I'm going to go to 100 hertz, turn that down. Okay, that's still good. Let me go to the 10 kilohertz range. Now I've just got to increase the output on the signal generator a bit because it's dropped off. We need to maintain 3 volts going into the input of this transformer. So just turn that up a little bit, 3 volts. Right, we're at 37 millivolts now. So this is our F1, this is our lower cutoff frequency, which is now 12.1 hertz. Very low, isn't it? So if we take our F1 frequency from our F2, well, it's 12 hertz and 12 kilohertz. It's hardly worth doing. So our audio bandwidth, it's about 12 kilohertz for this transformer. Now the final test that I'm going to do is a very important function of a transformer is actually to present the right impedance to the valve, to the output valve. Now the valve that we're using, the UL41 is from memory. The optimum load impedance, depending on which data sheet you read, is anywhere between 3 kilo ohm and I think it's 4.3 kilo ohm. Seems to be somewhat of a movable feast, but it's in that range. So what we actually want is, or what we're saying is, when the valve connects to the primary of this transformer, it's actually expected to see something around 3 kilo ohm. But to actually get that reading, we need a speaker connected to it, or in fact even better, we want a dummy load, and that dummy load needs to be the same speaker impedance as what we're actually going to be using on the radio it's connected to. So to simulate our 3 ohm loudspeaker, I'm actually going to use this resistance decade box. Now this one is actually quite a good one. It's actually designed to be non-inductive, and it's quite a good representation for our speaker dummy load. Now unfortunately these clip leads are quite long. We'd actually be better using something a little bit shorter, because they're all adding to the resistance of the test, and it's quite a precise measurement this, so ideally I'd use some short stiffer leads, but I've got nothing to hand, so we're going to use what we've got. So I just need to check, yes, our decade box, it's set to 3 ohms. So now let's just connect up to our primary side, our impedance meter. And in a perfect world, what we would be gunning for is it's around 3 kilo ohms, but I suspect we're not going to get that lucky. So there you go, 6.8. So I'm actually about double what we was aiming for. Now I've got to admit, I really can't explain that. I've actually built a couple of transformers so far, and both of them have come out when I've done this impedance measurements. They've come out about twice the value of what I was expecting, and I'm afraid I can't really explain why we're getting that. All I can say is that when we unwound the original transformer, we counted the number of turns very carefully, and I've also matched the wire gauge exactly, and I don't think it would make any difference kind of how I wound it. I mean, I'm sure that when it was wound originally by a machine in the factory, it was a neater winding, but I don't think that's the reason that we're getting this difference. So I can't really explain it, but I actually don't think it's going to make a lot of difference. One really good thing about valve output stages, valve amplifiers, is within quite a large margin they really don't care very much. Well, as you can see, in the last hour we've actually gone from a bag of kind of bits of old wire and windings and E-cores and yeah, horrible waxy gooey stuff to what looks like quite a presentable new looking transformer. Now, is it going to perform in the actual radio it's designed to work in? I've got to admit, I think it probably will. So I'll be very excited to actually get this sent off to Graham, RadioCruncher, and watch him install this on his channel. So I think for today though, and until next time, that'll do. Thanks everybody, bye bye for now.
Hello there. Hey, you gonna keep all them cakes to yourself?